All right. So once again, so thanks for inviting me here. So so as you'll see very quickly, I'm from the kind of quantum magnetism part of the community, and I've learned a lot while here, and there are interesting, very stimulating connections. But I'll try to actually comment a bit more. But so I also been asked by many people, what is it like life in Utah? And so here what we do on weekends. And it's really amazing outdoors place. And it's a big city in the Wild West. And so highly recommend it. Okay, so the work I'm going to describe, so builds on collaborations, extended collaborations that I had over years with Leon Valens at KATP and Andrei Chubukov, who is now at Minnesota, and Jason Alicia when he was, I think, at least most of that we did when he was still at Irvine. Okay, and so the very general motivation for my talk is to present kind of a view of composite or exotic order parameters, which are, kind of halfway between the ordered phases, say, such as ferromagnet or antiferromagnet, and in last really 20 or 25 years, the extensive search for quantum spin liquid, which has been very fruitful and essentially shaped quantum magnetism community within last decades, as I said. So along the way from here to there, we, experimentalists and theorists alike have stumbled upon, I think, several very interesting cases of ordered but non-trivial magnetic structures, and which are characterized by hidden order. And that, okay, so for example, something like this tensor built of bilinear and spin operators, and one can have higher powers. And depending on physical situations, these have different physical meaning. But in my view, a lot of that goes back to Jacques Villain, who have noticed long ago that basically introduced chirality and understood that because of it was scalar chirality to be precise. No, vector chirality, sorry, to be precise, and understood that being an Ising-like variable, chirality can order while spin disordered. Okay, and this has long, you'll see it again and again. And then, Andreev and Grishuk had very nice, very detailed classification of these kind of orders early on. And so this is a field where, not surprisingly, number of theoretical works vastly exceeds experimental systems. But in recent years, we had some convergence. And but before
by the way, I couldn't read the reference to that Villain paper.
The Villain, yeah. So I can give you it's in Journal de Physique 38. I can give it to you.
That's probably close enough.
And so, but what I wanted to, so just sitting here and listening to talks in the conference, I was trying to understand for myself what it makes kind of very loosely and broadly defined quantum magnetism different from spintronics. And for myself, I boiled it to this sentence that in quantum magnetism, spin is almost conserved. I mean, we do talk about anisotropies and Zoloshinsky-Marie or some other things, but they're usually in most of the systems that we study, those are very, very small relative to main exchange integral, whereas in spintronics, as I understood, it's not necessarily a case. So, I mean, the mechanisms are different. So essentially, in things that I'm going to describe, we don't think about dipolar interactions. Spin ice, of course, is famous exception from that. So it basically involves large moments, and it's important. Then in most of the systems, we don't, in our part of the world, in quantum magnetism, we don't think about coupling two phonons. Again, so I do, well, we do think, but okay, it doesn't seem to play a crucial role. But so I noticed a couple of months ago, there was an interesting paper, experimental paper over summer, which actually where this coupling plays a prominent role in that it seems to be crucial for understanding the lifetime of magnets. And that there is a very interesting general point that this paper makes. But then, as far as transport is concerned, most of it is restricted to thermal, and we heard several nice discussions of that yesterday, and there are a couple of experimental papers that about that. But so there is no almost no spin current in a sense that it has been discussed here by Spintronics community, of course, except that it all changed on the first day of the conference when Saito-san have shown that one can now do spin currents in the magnetic insulators, quantum magnetic insulators, the way I have defined them. Okay, so I think there are very interesting connections. But so let me go on with my talk. It's an ambitious plan, and I probably will not get through it, but I would like to discuss at least to get a long way. And so as a way, so I'm gonna talk about Bose-Einstein condensation of magnets, mention few materials, and then proceed with theory part. And so I do plan to describe this Lifshitz point theory in some details, and but so kind of in physical way in a way which I'll explain later on. This can be sort of a theory of BCS superconductors of magnets, and then if I'll have time, I would like to mention a very different problem in which even more exotic state of paired magnets appears, and it relates along the way. I'll try to connect to the things commonly discussed here. Okay, so Bose-Einstein condensation of magnets is very well known, and we just previous talk by Peter have shown dispersion very similar to this one. But so the way it emerges, this type of problems emerge in quantum magnetism is simply by virtue of having frustrated interactions. So it's localized spins living on some complicated lattice, not necessarily very complicated, but triangular lattice or Kagome or things of this sort. And then if you go to fully polarized state where the ground state is trivial, fully polarized, but then just look for single particle dispersion, for magnet dispersion, you'll see frustration shows up by the presence of several, in the simplest case, two or more, two degenerate minima. It can be degenerate lines. In case of Kagome geometry, it's a completely flat band, which is dispersionless. I think two of them are dispersionless. But so there's a minimal example. So we have degenerate spectrum where q and minus q are different wave vectors not connected by the lattice, so they're distinct. And so as we now magnetic field, spin is conserved, so magnetic field comes in the way of chemical potential. I can measure it from saturation field, where the saturation field is a field that fully polarizes all my spins. And so if my field is greater than saturation, then I have finite energy. The minimal energy state has finite energy, but then when I'm at saturation, the system condenses, so I have magnets touch zero, and at this point we have condensation. So point is that already here, so we can have condensation of two kinds. One is that magnet spontaneously selects plus or minus q point to condense, and so this condensation then, so the ground state is characterized by finite expectation value like this at some given momentum, and translated into spin language, it's a con state where so we have magnetization, which is spin tilt but so the xy projection of the spin carries momentum q, so it's a spiral, so it's a cone state or spiral in magnetic language. And so.
Can I ask a question? Is this are these two minima or is the ring of minima?
No. So right now it's only two minima. Yeah, ring is possible, but much more complicated. Yeah. So the symmetries we break are U1, I mean just selection of order on some particular, but then also Z2, which is chirality, right? So we spontaneously select between plus Q and minus Q, and that's a sense in which spins rotate. Another scenario is that we have single Magnon condensation, but in coherent superposition at plus and minus Q points, and that's something. So again, Peter mentioned it's an open, I guess, question in the Higgs material experiments. But so such condensation means we have something at plus Q and something at minus Q. And they actually equal. And so if you work out what it means for spins, it's actually super solid. Okay, so you break xy, U1 symmetry by selecting a direction in xy plane perpendicular to the magnetic field, but then your spins in magnetic language, so you selected this plane, and as you go from one side to another, they tilt, they cover some angular distribution called fan structure in classical magnetic language, but in terms of density and phase, it's a super solid because you have spin of finite magnitude, and since Sz can take several different values, so density is modulated at twice the momentum the phase is modulated. So it's a super solid. Okay, and interestingly, so it's not a small effect. So entire magnetization curve of triangular lattice antiferromagnet is determined by double Q condensation. So the fact that magnetization, and I'll come back to that if I have time towards the end of the talk, the fact that spin half or spin S antiferromagnet on square lattice, zero temperature, you measure magnetization, and it follows this black curve, and the most remarkable feature, which is the presence of magnetization plateau at 1/3 of total maximum magnetization. And this is very different from magnetization of a cone state or single Q condensate. And it's so this particular system happens to realize this magnetization curve, and it's purely quantum effect. Okay, and there are materials which show this beautifully. Okay, and so which of the two condensate takes place is determined by energetics. So there are these coefficients gamma 1, gamma 2 describing interaction of condensate at different minima and at the same minima. And but in case of, again, triangular geometry, the difference between these two is 1/s effect, so it's quantum effect. Okay. So, but today I'm going to really talk about something else, and it's a condensation of Magnon pairs. Okay. So in addition, both of the two previous condensates involved spin 1 flip, and now I would like to describe a system, a very simple system, in which we have pairs of magnons coming down. Okay, and if you go through the calculation, and essentially requires that there is a bound state of two magnons, and you require you calculate it, which is characterized by dispersion by center of mass, and so it's two spins flipped, so there is factor of 2, and if minimum of this energy is less than minimum of twice the single magnon, you can work out what happens, and you find that saturation field, so the field at which condensation occurs, or chemical potential if you want, for the pair is higher, and we are going from fully polarized state, right? So think of going from very high field to reducing the field, and so before you hit single particle instability, which is blue line, you hit two particle instability, which is condensation of magnons. Okay, and so this realizes spin nematic. It's a probably minimal realization of that, in a sense that your order parameter is bilinear in spin. You can write it in tensor notations if you want. So single particle excitations have finite energy. So if you look on spin-spin correlation function, either in real space or in momentum space, by doing neutron scattering, you'll find that it's short-ranged. So there is finite, it takes finite energy to break a Magnon pair. But the state does break U1 symmetry, but essentially you cannot see it by usual spin probes just because most of the probes we have coupled to spin 1 type excitation and not spin 2. And this is a spin 2 thing. Okay? And so the way to think about, I mean, one of the ways to think about it in usual polar coordinates, you think so something like this is finite, you work it out what it is, and so you can think of a state in which angle theta dynamically fluctuates. So the spins form in fan state, but then in that plane they constantly move, so the time averaged for a single spin is 0, but for the product of spins on a bond, it's finite. Okay? And that would be spin nematic. Okay? And so before I get...
That kind of state common?
Well, so in theory or in experiment? So I'm getting to that. So it's ongoing investigation, and so we still, okay, so to give away, so we still cannot know, so no spin nematic has been detected unambiguously experimentally, but so we do know, okay, in where to look. And so, for example, so list of material, so the simplest realization of this physics, and I'll come back to that, okay, shortly, is toy model really, which is J1, J2 model of chain, sorry, J1, J2 chain of spin S, but you require J1 to be ferromagnetic, negative in this notation, and J2 antiferromagnetic. Okay, and so the way basically to think that negative exchange, so it provides for some kind of real space attraction between spin flips. So okay, so it's attraction which explains why bound states are there at all in first place and why they are lowest in energy. But so it turns out that there is, the list is not complete, taken from this work, and it's probably few materials have been added to it recently. But so there are materials which seem to satisfy these conditions, and there are active experimental studies of those. And so there is one of these goes under the name of linearate, and on Monday, I was at ETH talking to Andrei Zholodyev, who is a neutron scatterer there, and they studied this particular material. And so the hope, but there are hints, but there is no proof that there are this phase 5 in this complicated diagram of this material can be maybe nematic. Okay, but there is no. Okay, it's certainly far from clear, and. Then there is another material. Okay, so it's a quantum spin. So spin is taken spin half on coppers, and again chains which are formed by virtue of crystal structure, and they are weakly coupled. And this material has been studied for last probably about 10 years extensively. And I'll say a couple of words. So its magnetization curve. So what attracted everybody's attention a few years back is that magnetization curve, as you go from fully saturated, so high magnetic fields, which are really high, about 40 Tesla, you go down, reduce, and there is this kink, and we knew from, so that this is a candidate material for this negative J1, positive J2 chain. And so this kink was originally interpreted as maybe being a nematic because there is another kink here at lower field, and then, But, unfortunately, current understanding is that this first kink, which was taken as a signal of nematic, is probably due to disorder effect. There is still ongoing research. But what is known that a state in this huge interval of magnetic fields from about 10 Tesla to almost 40 is very unusual and can be understood and fully described theoretically and both experimentally as a spin density wave formed by Magnon pairs, not by single magnons, by Magnon pairs. And so NMR line shape, I can discuss it in much more details after the talk, is very specific to this type of order. And this is an interesting order because it preserves symmetry of rotation about magnetic field. and there are supporting neutron scattering measurements. So this material is really has been a best bet for this pneumatic phase, but most kind of, it's not the most recent paper, but so the range of the fields in which pneumatic can be present has been experimentally reduced to the interval of about 1 Tesla. It's a very high field, and okay, so whether or not something will be found there remains an open question. And finally, there is a very different material. So I'm just, it's a last material that I want to mention. So nothing is definite, but it's a very different geometry. It's Kagome geometry, a complicated one, but it happens to be so that even though lattice magnetic ions form, which are again, coppers, and then name, it's a mineral, so it goes under the name of Albrasite. Okay, but it's spin half Kagome antiferromagnet, or so we thought, but then with exchange interaction of the order of 100 Kelvin, huge scale, but then it shows after 10 years or maybe 15 years of experimental and theoretical studies, it turned out that it has huge magnetization plateau, again at 1/3. And this plateau was completely missed in previous 10 years of experimental work. So it just material quality is crucial. So, you know, this was discussed in 2000 as a candidate for spin liquid, and now we are discussing as the biggest magnetization plateau ever observed in quantum magnet. It can be as wide as 70 Tesla by some estimates. So it's really huge effect. But spins are very quantum. And the NMR studies from Takegawa in Tokyo, Takegawa's group in Tokyo show there is plateau. Then there is a, in blue shown, it's a NMR line shape. So which is actually very similar to one observed in spin density wave state of liter copper vanadium oxide I just showed on the previous page. And in between there is something, the signal in red. We don't know what it is, but experimentalists tentatively denote it as this phase as N, maybe unknown and maybe pneumatic. And so the work is still on. Yes.
Go back.
Yes.
Why do you call this a 1/3 magnetization plateau? Do we know that it would have full magnetization, which is?
Well, we don't know. So we know that. Okay. So all measurements are consistent with spin half coming from copper. So you know what the saturation magnetization should be. And so what is observed is roughly. I mean, it's not quite, but so it's a, you know, somewhere near 1/3 of that.
But you would expect that at some point, if you go higher with the field.
Oh, so you go right. So the I showed. So you are sit on the plateau, and then at some yet higher field you ramp up again. So you go up.
What would it be in this material?
Oh, you mean the field?
Yeah.
Oh, okay. So right. Okay. So I
can call it a plateau when it looks like saturation.
Right. So okay. So unpublished data from Takegawa and collaborators in Japan suggests that above 100 Tesla. Okay, they see that it's not a plateau. It's starting coming up, but it's such a field. Yeah. Oh, okay. Yes, I mean it's a.
Yeah, you can think of this B as like a chemical potential for flip spins, or
yes.
yeah. So it's like a gap.
Yes.
So it's not that.
So it's
crazy. It's not a crazy thing.
But it's the range of that particular plateau is crazy. Yes. And so interesting point that if you so what is the connection? Why I'm describing this material is that if you think, and there are much more detailed theoretical considerations which I don't have to describe, but kind of in a very simple way, what can be the structure of such 1/3, taking that it's 1/3, a magnetization plateau. It's very simple. I mean, one possible candidate state, which is selected by more delicate theoretical consideration, is that you fully polarize spin on chain. So this is Kagome lattice. So the blue spins are fully up, and the yellow, which are interchain in that notation, are down. And so there are 3 spins per unit cell, 2 up, 1 down. That gives you a plateau. Okay. So if there is a connection, if the low density, the low field phase below the plateau, okay, And the plateau, by the way, is at 26 Tesla, or something like that. And I already said exchange integral is of order 100 Tesla and 100 Kelvin, sorry. Okay, almost the same as 100 Tesla. And if you think how is it possible, so if you just do very simple back of the envelope estimate, you know that it cannot be only antiferromagnetic exchange. There must be some ferromagnetic or negative exchange, so that the field required to flip is actually much smaller than 100 Kelvin. Okay, and so, but so the fact that the low field phase shows phenomenology, at least as far as NMR experiments go, which is very much consistent with spin density wave I mentioned before, suggests that we can maybe understand this phase as a condensation of bound states of magnets, and in which case this question mark red phase would indeed be pneumatic. Okay, and it's unlike the previous material, it's in the field range. Okay, still high, but 20-something Tesla, which is doable, and so there is a lot of research going on right now. But so let me so there are hints of the materials that may realize this physics. But so let me now go to kind of formulating our basic understanding of this system. So we are thinking about, again, J1, J2 chain with negative ferromagnetic J1. Okay, and so if thinking classically, so what is the ground state? So it's easy. Classically, it's easy to find out. So if J1 is much greater than J2 or J2 is small, then we simply have ferromagnet. Okay, it's an exact ground state. That fact remains true for quantum model as well. It's an exact ground state. So plotted as a function of J2 over J2 plus absolute value of J1. So there is a critical point at 1/5 in this coordinate at which ferromagnet becomes unstable towards, and so the state at higher ratio of J2 to J1 is some kind of spiral, okay, incommensurate spiral. So, so magnetization is 0, so it averages out. Okay, so if you think in a bit more details, so in terms of dispersion, spin wave dispersion, so in a ferromagnet, energy of elementary excitation goes as momentum squared. In this spiral state, it's almost an antiferromagnet, which has two minima at incommensurate momenta, which are determined by the ratio of J2 to J1. And so it's a linear spectrum, kind of, which is typical for antiferromagnets, relativistic kind of. But at that critical point, which is the Lifshitz point of the theory, stiffness of the ferromagnetic state goes to 0, and so dispersion goes as k to the 4. And so that's what will define the quantum Lifshitz point. So it's a point at which leading term in the spin wave expansion, if you want, of the energy vanishes, and system develops k to the 4. And then as you go to greater J2 over J1, the minima develop at finite momentum. Okay, and I'll, okay. So, so now we add to that axis magnetic field, and so ask, what is the magnetic field needed to fully polarize the system. So when we are in ferromagnetic phase, that field is 0. It's already fully polarized. But as we go past this Lifshitz point, so it takes some finite magnetic field. And so if we above that field, so and calculate dispersion in such a state, then we'll have this curve with two minima, which I showed before. Okay, and then it turns out, and I'll show a couple of numerical. Okay, analytically, it can be also worked out calculations which show that as you go down from this fully polarized phase to low field phase, what happens, you observe condensation of two magnets. So as a function of range of this parameter. So right, for a given range, so you go, and here you'll condense two magnets. If you move closer to Lifshitz point, you condense 3. Then you condense 4. So you condense in molecules with quantum numbers, as Z2, 3, 4, and maybe more. Okay, And so these are called as multipolar phases. These are phases which are described by complicated tensor order parameters, and for which excitations with such as usual spin waves are absent, because that takes finite energy to break a bound state of pairs. Okay? And so numerically, so one of the first work was actually by Fabian Heinrich Mössner, who was here yesterday. So, and numerically, it's relatively simple to see that there is Magnon binding, because if you look on magnetization curve in a finite system, so magnetization changes in steps, and what they observed that in some range of parameters, the steps by which magnetization changes is not 1 but 2. And then this was followed by more extensive work from Furusaki's group in Japan, and they observed that there can be 2 Magnon condensation, there can be 3 Magnon condensation, 4 Magnon condensation. Okay. So, and final ingredient that I need in order to proceed with some analytical description is that another numerical study from Andreas Leuschli's group have found that so this data, which is plotted as J1 to J2 ratio. So when it's J1 is negative, so when it's -4, to the left of that point is ferromagnetic ground state, and vertical axis is magnetization here. And so if you at some particular J1 over J2, say -2, as you go from highest fully saturated state down, reducing magnetic field, you condense into this paired Magnon state condensate of 2 Magnon pairs. If you are at, say, -3, you condense in condensate of 3 Magnons, and then at 4. But then this doesn't continue. If you move below closer than some critical value, you actually have metamagnetic first order transition collapse. Okay? And that is okay, I show it because we think it's an important piece of physics. Similar but much less detailed numerical study of 2-dimensional J1, J2 model, where J1 is ferromagnetic and J2 antiferromagnetic, seems to, from these people, also, okay, it's from their paper, shows that as you go from fully saturated polarized phase to low field phase, so in some range of parameters in the vicinity of Lifshitz point in 2 dimensions, there is first order transition, which then changes by continuous second order transition. And so we would like to describe this kind of, to find present a universal description of this physics, which would take into account the fact that there is a Lifshitz point, that there is a, depending on where you are, you have a either discontinuous or continuous transition. And so, and since Lifshitz point, so by very definition, means spin state with very small momentum, so spiral with very, very long wavelengths. So we want to formulate the theory in terms of nonlinear sigma model, that is theory for unit vector M, which is magnetization. Okay. And so here we're writing it. So we are now, from this point on, we are not analyzing specific lattice model. We are, based on symmetry arguments, postulate this action and then see what we get from it. Okay? But the action has unknown parameters, which, okay. So let's look on terms with derivatives first. So since variation is very slow, so we expand that gradient expansion in derivatives should be a good expansion. That's a basic physical assumption. So then the first term describes stiffness, if you want, of ferromagnetic state. So when delta parameter is proportional to the distance to the Lifshitz point. If it's positive, that just k² if you Fourier transform. So that's what we expect in ferromagnet. But we know that it can change sign. When it becomes negative, we need to high order terms to stabilize the thing. Okay, so that's this term with coefficient k. So that it describes k to the 4 dispersion at exactly Lifshitz point when delta is 0. But then if we have written term with 4 derivatives, there is another term which we can write, which also contains 4 derivatives. But this guy, so if you look closely, is quadratic in field M, whereas the new term which we add is quartic in both derivative and the field M. And so it describes interaction. It's a nonlinear term, okay, in all senses. Okay? And it turns out that this term, which is crucial for the physics, and it was absent in previous attempts. Then there is magnetic field, and finally the very first term is a Berry phase, which, for which we also heard this talk this morning. But so it's coming from it's almost ferromagnetic state. What is important, so it contains first derivative in time. And so if you Fourier transform, forget about nonlinear term, and transform, you'll get the frequency in first power from this term, and k to the second power, and k to the fourth from that term, and that describes, as far as non-interacting spin waves, kind of all ranges that I've shown. But point is, you cannot get far without thinking about interactions. Yes.
So if you tune the system to the Lifshitz point,
yes,
and classify the higher order terms according to relevance in the renormalization group sense, can you show actually that higher order, like 6th power of field, is irrelevant?
Yes. Yeah.
So that's all. That's only
Right.
the relevant and marginal stuff you
Right.
repeat.
Yes.
I see.
Okay, and so this section has a very interesting and really unique, very special, not unique, but very special property, is that
You don't put any anisotropy.
so we want to, yes, I mean, it can be added, but it will add number of terms, you'll have to. So no, we didn't put.
Would it change the physics?
Huh?
Would it change the physics?
So, okay, so the studies, at least numerical studies that I've shown, are all done for Heisenberg model.
Okay.
So that's, okay.
Yeah.
But so I think anisotropy of XXZ type, so that Ising-like, is easy to add. More complicated anisotropies will mess that significant. Right, and so, okay.
Just last question. I mean, is there actually an underlying order from which you
Sorry?
start? Is there an underlying order from which you start to build that model?
No, we are just thinking that all we require is that expansion and derivatives make sense, right? So that's an assumption.
But you have an anti-ferromagnetic coupling in there, right?
There is ferro and antiferro.
Right. And
So
the
depend.
anti-ferro does not lead to a rapid change of the magnetization.
But so we are near Lifshitz point, right? The Lifshitz point is that's the key. The key. So in ferromagnet, we minimum is at k equals 0. At Lifshitz, the same at Lifshitz point, right? And then as we move away, so as long as we are close to here, the location of this minima is very close to the origin. So everything is extremely smooth. So there is no, we are not, I mean, we are very far from something like momentum pi or any. Okay, so that's what defines Lifshitz point. That's why we write this derivative expansion. But so so this is a little bit technical, but if you bear with me. So this whole thing can be rescaled as shown. You can rescale space and time, as written, and then observe remarkable feature that the action takes completely dimensionless form. All coefficients except for the interaction term, which was u here, and now is denoted by v, which is just u divided by k, that thing. Okay, so everything else scaled out. Magnetic field is in some scaled units, but that's not complicated. And so it's completely universal thing. And the k over square root of delta, and delta measures distance to this Lifshitz point in parameter space, right, comes in front. And so as we approach Lifshitz point, this gets large, it diverges. And so semi-classical expansion should be very good. It's like expanding, semi-classics in quantum mechanics, expanding in powers of Planck's constant. Okay, so we know that analysis, if for sufficiently small delta, we essentially, saddle point analysis should be almost exact. Okay, so important question is, what is this coefficient V, which is rescaled interaction? Okay, we can put some. Okay, I don't have time for that to describe, but so there is stability analysis which shows that interestingly V can be negative. It only has to be greater than -1 in these dimensionless units. Okay, and it's an important point because we'll see that physical system where we can make a connection characterized by negative V, and that system is just J1, J2 chain with spin S. And so we do Laplace expansion, and we match prediction of the field theory with lattice calculation. And when kind of all is done, we find that that coefficient V is -3/2S. So when S is infinite, which is, interaction disappears, which makes sense. But so it's a quantum effect of that interaction. Okay, and then so at this point, so assuming that we are very close to Lifshitz point, we can start by doing. So we are interested in a phase which develops below. So we reduce in magnetic field and ask what happens as we go from fully polarized phase, which is very simple. In fully polarized phase, forgot to mention it, vector M has structure 0, 0, 1, so there is fully polarized along the axis. But so we are interested what happens as we reduce magnetic field. And so at this point, we essentially we can forget about, at first, it will come back, quantum mechanics and minimize energy. That's a saddle point solution. And we tried various things, but the best what we could find is the con state, or in my previous single Q condensate, in which spins, Z component is reduced. So order parameter is psi, transverse magnitude of transverse vector. And then depending on chirality, so the solution with plus or minus means chirality. Okay, and so having the structure, we can find energy, minimize it, so everything. So because of this quartic term, it's more complicated than it sounds because equations are nonlinear, but we can solve them. And what we find is that the physics depends crucially on magnitude of parameter V, this dimensionless interaction. Namely, if, and I'll have it on next slide. So if V is small in absolute value, it's actually negative. There is minus sign somewhere missing. So if V is small in absolute value, then we go from fully polarized state to this con state in a continuous fashion. But once it exceeds critical number, the transition is discontinuous first order. So magnetization changes by finite fraction in thermodynamic limit. So it's a metamagnetism. So that critical number happens to be -1/4. So if V is greater than -1/4, then we have continuous transition, so magnetization changes in continuous way, for example. If V is less than 1/4 but greater than -1, it's a first order transition which takes place at the field which is greater. So this red curve is above the blue curve. Okay, so it's a discontinuous first order transition. Okay. At this point, a very interesting connection can be made with extensive numerical and DMRG and combined analytical studies, which again involved Fabian and other people. So I told you before that for spin S chain, we know what V is, and so requiring that it's less than -1/4 tells us that there is critical value of spin, which is 6, okay, which is not particularly small, but it's a critical value of spin. If you have chain with spin less than 6, the transition is discontinuous first order. If we have chain with spin 7, it's continuous. Okay, and this follows from our analysis. And amazingly, these two papers, which go through really many pages of completely different calculations, find critical value of spin either 5 or 6, depending on precisely how they do the calculation. Okay, so there is a nice connection. But more importantly, so what we find, if so V is determined by microscopic Hamiltonian. So for spin S, J1, J2 chain, we can fix it. We don't know what it is for spin half chain, for example. We can make guesses, but there is really, we don't have a way to compare it, to evaluate it. But so whatever it is, V is given for a given microscopic model. And so if it's less than -1 over 4, then all our theory predicts up to now is that the transition from fully polarized state should be discontinuous. In numerics, I remind you, so there is region of first order transition, which is then replaced by multi-Magnon condensate continuous transitions. Okay? So the question is if this is contained in our model, and the answer is yes. I will not say much, but so essentially what we need to do, add quantum fluctuations to our saddle point, and so we do that, and it turns out, so we do it in this, so we find the saddle point, we know the configuration, we know pitch of the spiral, we know magnetization, all of that, and then we quantize, add fluctuations on top of that, and minimize quantum energy correction to the classical energy. And in this way we find really that this red curve, which was, so now I'm, okay, at some point, let's see, yeah, pay attention. So I was finding before, showing just to make clear. So H versus delta, is parabola, goes as delta squared basically. When I plot it as function of delta squared, it becomes straight line. So just, okay. And so when plotted as, so when we put classical plus quantum fluctuations, we find that this red line actually bends over and crosses the line of single Magnon transition, continuous transitions. Okay, so yes.
So I missed actually when you introduced the quantum fluctuations. What distinguishes quantum from classical fluctuations?
No. So we find field below critical. We know that M is in this const state, right? And now we know classical configuration, and now we add quantum fluctuation to that. So we quantize with respect to this rotating quantization axis, and so we add semi-classically assuming we can do that. Okay, we just.
So you just take the fluctuations into account.
Yes, quadratic fluctuations, but they are non-diagonal, so there are anomalous terms. And
but why do you call them quantum?
Because they are. I mean, so.
I mean, in your class, you have a classical model.
No. So the model is not. So no. Here there is time derivatives. This Berry phase knows about quantum mechanics. It's a dynamic problem.
But only if you take into account binding models.
Yeah.
No, well, okay. So there are maybe some topological. So we are not doing that, but there is quantum. So dispersion of excitations on. So we have non-trivial kind of, well, I mean simple, but okay, twisted classical configuration of magnetization. And now we're asking what are excitations, right? And so for that you need to add quantize the same as we do with phonons, with lattice. We have equilibrium structure and then we quantize it. So there are, but since it's a non-collinear structure, so it's not a ferromagnet anymore, the quantum fluctuations change the energy. So the true ground state of the quantum problem is classical plus quantum and the mixture. And we are evaluating it approximately.
So maybe they can, sorry.
I was going to say, if I think of it as a spin coherent state path integral, then this energy functional is sort of the coherent state expectation value of the spin function.
Yes. So we just say spin, it's what's written is Hallstein-Primakov, if you kind of look on that, applied, specified for unit vector, but the axis of quantization is our saddle point solution. So we kind of boost into this rotating frame and quantize. It's nothing unusual. We are not doing anything unusual.
Of course, I understand the procedure. The question is, it's just to say, that your Berry phase term is of course needed in order to get the classical lambda Lifshitz.
Yes.
Right? It's not.
Yes.
It's not just
right.
quantum.
Yes.
It's necessary because it's the conjugate
well,
variable in it. Now
sure.
the question is the fluctuations which you're looking at. These are spin waves.
Yes.
And spin waves, they can also have a classical character. I mean, we heard it also
But-
in his talk, right? And so I'm asking now, is there kind of a measure of the quantumness of these fluctuations?
Well, so
like
the-
H-bar or something like this?
Well, the H bar is hidden in parameters, delta K and all that, V, and that's first. And secondly, so the amount. So if there were no, if it were a uniform state, so ferromagnet, for example, right? We would find then in the ground state expectation value of spin waves is 0. So there are no it's an exact state. But here, doing this procedure, we find that it actually changes. So
I understand. I mean, I'm arguing about that. It's just a question of language. I mean, you take fluctuations into account, but you say the fluctuations automatically are quantum fluctuations.
Well, because there is no temperature in that thing. But
Okay.
So the conclusion is the Landau-Lifshitz equation is quantum.
Yeah.
yes, no, I mean,
At zero temperature.
It
depends
is.
on what you calculate, right?
Sorry?
It depends on what you calculate. If you calculate the expectation by the ground state magnons, that is quantum. But if you calculate the electricity of the magnons, that somehow also contains U and V factors, but that is in principle classic. So I think
okay.
it's sort of depending on what you calculate.
So we are calculating ground state, essentially comparing ground state energy of fully polarized phase with a phase which has finite twist. And my claim is the fully polarized phase has no quantum fluctuations, but the phase with twist has them. And this is approximate way to take them into account. It's not an exact. I'm not claiming exact solution. I'm claiming iterative solution. So you find classical configuration. So in antiferromagnet, that would be, say, simple Niel state, right? How we find it? By minimizing classical energy, say, and spin up and down that. And then we add quantum fluctuations to that, and we find that magnetization is reduced, for example, right? So that's analog of that procedure. So nothing unusual here. So if you then ask what is the ground state, it's not just, in case of antiferromagnet, it's not just up-down. You have a mixture of much more complicated patterns. That's the same here.
I think, I think the dispute revolves around this issue of binding numbers and direction. If you have coherent states, and you know that classically, you take a classical dynamics if you don't take into account binding numbers, right? And the system becomes more and more quantum if you actually allow the field to wrap around in configuration space in any time
So
direction.
I understand what you're saying, but so let me proceed because I want to finish this part of the story and then we'll discuss. So
10 minutes including discussions.
you mean 10 minutes from now? You're saying?
From now.
Okay. Well, okay. So
shut up.
so
We all suffer though as well in our talks.
I'm just okay. So there is the end of the story is much more interesting. Let me claim that. And, so with this, let me insist, quantum fluctuations approximately taken into account, the energy, the phase transition line separating polarized state from the con state, first order transition line bends over and crosses this dashed red line, blue line, sorry, which is a line where single Magnon energy, goes to 0. So just okay, it's a, and so which means, and this happens in some critical delta C, which we can calculate within our theory, and that importantly that delta C depends on spin. Okay, so right, so that if we now again for a given set of parameters, happen to be at delta, in that range. So as we go down, there is a metamagnetic transition, magnetization jumps, and okay, if we are to the right of that point, it's a should be continuous transition. But at this point, we want to ask: is it really single Magnon condensation or something more interesting? So, like in numerics, can happen where we have this multi-Magnon molecules essentially condensed down, and so we cannot. Okay, so there is we don't have a full answer to this, but what we can do, and that's where I want to spend a couple of minutes, we can do within the same action. So we calculate exactly the 2 Magnon bound energy within our nonlinear sigma model. And so what this task is sufficiently non-trivial in a sense that Magnon dispersion, so we just trying to calculate what happens to 2 Magnon state if we are to the right of that delta C, so in the continuous range. Okay, Magnon dispersion is highly nonlinear, k to the 4 and quadratic. Interaction between magnons is also goes as in general, so it depends on incoming and transferred momentum and center of mass momentum, so they all couple, but so it's k to the 4 in general. So this is quite a technical task to carry that out, but what we find out, so we did that after struggling with it for a couple of months or so, and what we find is that there is another critical point or special point in this picture, which is delta C2, which is a point at which binding energy of 2 magnons goes to 0. Okay? And so there is a point where first order transition happens, there is a point where second order transition of 2 magnons, and now in this then to the right of delta C2, it's truly single Magnon condensate as far as we can tell. And so this tells us, so suggest the following picture. So this is our, again, phase diagram, tentative phase diagram in which we can fix 2 points. So there is a Lifshitz point, which we know exactly. There is a delta C critical distance, which is determined by parameters, again, of the microscopic Hamiltonian, which measures distance to that point. And so this dashed line means discontinuous first order transition. And there is delta C2, which is different from delta C, where to the left of which 2 Magnon bound states condense and realize pneumatic state. Now, so numeric suggests that there is 3, 4, and who knows what else. And so this we cannot calculate. I mean, we didn't calculate, so we put them just by analogy. And so, but all these phases are described by single nonlinear sigma model, which depends really on single non-trivial, I mean, in these full units, interaction parameter U, which we were able to fix in a single case of J1, J2 chain. And just, so I won't go further with remaining talk, but so just as a hint, if simple extension of that same one-dimensional action to 2 dimensions, say by adding derivative on y-axis, and so we still can in that 2-dimensional now sigma model, which we will describe some 2-dimensional Lifshitz point, do rescaling so that again all of the action can be written in highly universal form. There is still one interaction parameter which must determine the fate of the transition, and the prefactor of so rescaled action is still diverges as we approach a critical point. So we think that there is a broad class of problems which we can analyze from this point of view, and which rely on the smoothness of the magnetization deformation. And so this pneumatic phase is very interesting. So again, so it's a condensate of 2 magnons. It's kind of the way I think about it is really superconductor of Magnon pairs, so that there are no single Magnon excitations, but such a state breaks U1 symmetry, and so it has must have some currents which are yet to be determined, and the way how to couple to them and all this, I think, is a very interesting
so the angle momentum is twice h bar.
Right.
So
Yes.
in principle,
Yeah.
current.
Yes. Absolutely. So I stop here. There is a remaining part. Okay, the part about more exotic condensate, but okay, I'll be glad to discuss with you in private, but I don't have time to show it. Thank you.